Hello everyone, good morning. I'd like to start off by welcoming you all to Keele University for this 4th edition of our CCP-EM Spring Symposium. I'll start just by saying thank you to our sponsors, Molecular Dimensions, Agar Scientific and NVIDIA, for their generous support which has helped to enable this meeting to happen. And with that we'll get started with the What's New session. So we're starting with Tom Burnley to tell us what's new in the CCP-EM.
Thanks, Colin. Morning, everyone. So as Colin said, my name's Tom Burnley. I'm one of the 3 CCP-EM developers now, alongside Colin and Agnel Joseph, who's also here. And I just want to spend 20 minutes giving a quick introduction to what we do as an organization, and then focusing on our software suite that we've just released. So CCP-EM, as you should know, is the collaborative computational project for electron prior microscopy. And we aim to support users and developers in the computational aspects of biological EM. And so we have 3 principal aims that we try and fulfill. So we want to build a UK EM community by running events such as this. We want to support software users in training and in best practice of using the evolving algorithms. And we also want to support the developers of this software to help test and disseminate their work. So we thought perhaps the best way of doing this was to pool all of these new developments into one uniform package, the CCP-EM software suite. And as you may know, we've had a beta release of this going for a couple of years now, but we've finally released the version 1 of the CCP-EM software suite, and that's now available to download on our website. And this contains a suite of utilities for EM data processing and allows us to connect together a network of developers across the UK and now into Europe that I'll go through in a bit. As I said, you can download it from ccpem.ac.uk. It's designed to coexist with our sister project, CCP4. And you can get it for Linux or Mac platforms at the moment. In the future, we'll port it onto Windows as well, but we haven't done that yet. It's free for academic use, and it has a fee for commercial industrial use that's described on the site. So I thought I'd be brave and show you what it looks like. So this is how you get and run our software suite. So you download it as a tarball, you unpack it in the directory of your choosing, and then you install it using the install script, you source it, and off you go. So let's have a look. So here is one I made earlier. So I've already downloaded it to save the broadband here. So we just install CCP-EM, then we source, set up ccpem.sh, and then we should be good to go. So on the Mac, it will try and automatically find CCP4 for you. It looks for it in its environment. If you're running Linux, because the install might be in different locations, then you need to source the CCP4 setup file as well if you want to use some of the tools provided by CCP4, so things like refmac and molrep. Let me just hide that. So this is what you get. So you get a simple kind of project manager. For those of you interested, it's written in PyQt, the GUI display. So you get a simple project manager. You can set up different projects, different users. And then each project then gives you a hierarchy, a chronological list of jobs that you've run. Over here on this menu, you have a list of different tasks. And at the bottom, you have an information window that tells you about the settings and setup. And it also gives you an email contact if you have any bugs you'd like to report that me, Colin, and Agnel will get to. One useful feature is this test mode. So you can toggle this on and off. If it's toggled on, when you launch one of the tasks, so let's launch refmac, for instance, it will preload it with some test data, which will allow you to spin it over and see what it does. So as you can see, it's loaded everything in there. We can give it a title, and we hit the run button and off it goes. So whilst the task is running, it looks like this. So it gives a list of the stages in a particular job, and you can click through these stages, and as you can see, the output files from the different processes are displayed automatically for you and update as it's whirring around. There's a launcher file that highlights all the important files associated with that particular job, and allows you to look at them quickly in your molecular graphics viewer of choice. So you could look at it in Chimera, for example, and it will automatically load, in this case, the starting PDB prior to refinement and the refined PDB and the target map. It also has a results page. So this is for RefMac. This tells you it tells you the relevant statistics for that job. Here you can see that this is a test data set, so it's designed to run quickly rather than to completion. So you can see actually this needs to run a few more cycles to reach convergence. Okay, so that's the kind of general overview of the task interface. I should mention there's an info button, so you can click on this and this will take you to the relevant online documentation for each task. And each one of these task interfaces looks broadly similar. Okay, so that's kind of what it looks like. So what's inside it? So to begin with, we've kind of focused on providing tools for model building and refinement. So we've developed this model building pipeline, stitching together various different programs that I'll walk you through now. So starting with maps optimization. So we have as you should know, one of the first things you must do once you have a map from your 3D reconstruction is to take a look and optimize the sharpening coefficient that you apply to it. So we have a tool that does this for you, and so you can enter an array of sharpening B factors, and it will calculate these for you and show a Wilson plot so you can see the effects that this has. And this has quite an important effect on the quality of your map. So in certain circumstances, some of the deposited maps can be over-sharpened, and you can see these truncation effects at the resolution cutoff. And what you're looking for is a scenario where the amplitudes will tend to 0 at your expected resolution limit. This is what it actually has, the actual effect in real space, if you like. So you can see that optimizing the sharpening can have maximize the amount of data available in different locations. So it's critical you do this first before you go on to the downstream processing. So I should say that this is quite a simplistic way of doing map sharpening. There are other more sophisticated tools being developed, both in a Phoenix software package and also by Ian Jacobi from Delft in his log scale package that he'll tell you about later on. So at the moment, as this only applies a single B factor, one can expect local variation in different areas of your structure. So if you do it like this for the time being, you may need to have multiple different sharpened maps for different areas of your target map. So once you've got your map ready, you can start trying to dock models into it if they're available. So if you have a kind of medium to low resolution map, so let's say 5-6 angstroms or worse, then we have a tool that was developed by Alan Roseman at the University of Manchester called DocEM. And this performs an exhaustive 6-dimensional rigid body search for your target PDB into your experimental map. It then gives you you can target the region of interest. So if you know that, or you expect your PDB to be in a particular location, you can set that. And then it returns solutions ranked by correlation coefficient. And you can then view these different results in Chimera. At these kind of resolutions, we can't guarantee that the top hit will be best. So we recommend that you go through the top 10 or 20 hits, use your understanding of the system to pick the one that fits best. For higher resolution cases, so sort of 5 angstroms or better, then we use a CCP-4 tool called MoRep. This performs very fast docking. It can find multiple copies, so if you expect, say, 6 different copies in your map, it'll search for those. And it can also optimize your sequence. So if you're using a replacement model with a different sequence than the one you expect, you can give that sequence, it will perform an alignment for you, and it will truncate your reference model to your target sequence. What happens if you have no homology, you can't find a suitable one in the PDB, you don't have one from other experiments in your lab? You can use something called choice. If you have a weak homology model, you can use something called choice. And this is from Maya Toff at Birkbeck. This allows you to give a target sequence and a template structure, and it will align, build, and energy minimize a new structure for you. And we think this is going to be a useful kind of convenience feature for high-resolution modeling. So rather than you having to manually change 100, 200 side chains in Qt, you can do this as an initial pass and then start working with the correctly sequenced model. Okay, what happens if you don't have a model at all, just a sequence? Then you can use a CCP-4 tool that we've co-opted called Buccaneer to build amino acid sequences, or its sister algorithm Nautilus to build nucleic acid sequence. So you just provide it a map and a sequence, and it will do statistical chain tracing to build your map for you. And this works pretty well, especially at high resolution. So this is some test data from Scott Ho from the University of York and Kevin Cowton's group, who are the developers of this. And here they took the DANEV hemoglobin map out of the EMDB. And with the appropriate sharpening factors, they could build nearly all of this in 20 minutes. So it works nicely at a high resolution. They're optimizing the algorithm at the moment to extend the resolution range you can cater for. Okay, so now hopefully we have a model in the right place. What do we do next? So we work with Gareth Mushradov from the LMB in Cambridge with his program RefMac. And this is designed to perform structure refinement at high resolution. It was, of course, originally developed for crystallography and is part of the CCP-4 suite. And we've written an EM-specific wrapper that sits on top of that for high-resolution EM map refinement. So it performs a phased vector difference refinement in reciprocal space, and it has 2 different modes of operation. So it can run in a global or a local mode. So the global mode will take your whole map, all the models docked into it, and run it as a whole. But obviously, if you have a very large system, that can become unwieldy. So if you select the local refinement mode, what it will do is cut out your map around the PDB model that you've supplied and just refine that locality. It does a bunch of stuff under the hood that means you don't have to worry about converting from MRC format to MTZ formats. It will perform map sharpening for you if you ask it. It will also automatically find your model in your map. If you click on the Find in Map option, what that does is it runs the MoRep program I told you before in the background to place your model in the right place before it starts refinement. We can also call in additional restraints from Rob Nichols' ProSmart program to help at lower resolution. One of the important things that RefMac provides is Garib's half map validation. And the reason why this is important is we want to try and limit overfitting. So overfitting is where effectively you're fitting too many parameters in your model to your data. And this can be caused by having insufficient data due to low resolution or partial occupancy in domains, by ignoring data, by truncating the resolution, by suboptimal model parameterization, by bad weighting, so putting too much emphasis on your data and at the cost of listening to your stereochemical restraints, or just a simple kind of excess of imagination by the user. So what half map validation does is to try and show you if you've entered into this situation. So what we do is we perform the normal refinement on your whole map, Then you also input your two half maps from your reconstruction. The refinement protocol is then performed again against one of the half maps, and then it's compared against, that output is then compared against the other half map, which the algorithm hasn't seen. In the case where your data fits properly, then you should see this. So you don't see a big deviation in your Fourier shell correlation between your free half map and your working half map. If you're overfitting, then you start to see divergence here, and this is what you want to avoid. Okay, so obviously not everything that goes in the EMDB is super high resolution. Many maps, in fact most maps, are worse than 5 angstroms. So we've provided some tools from Maya Toff at Birkbeck. So she's developed an algorithm called FlexEM, and its assistant application RibFind. And what this does is it allows you to do flexible fitting of rigid body domains into EM maps. So it works best at sort of medium resolution. What it does is you give a set of rigid body definitions, so secondary structure elements, for example, and then it performs a real space MD refinement to push those blocks of your structure into the map. So for this, obviously, it requires rigid body definitions, and then we have this helper program called RibFind, which allows you to define these secondary structure elements. Also within CCP-EM is a bunch of other tools that we're sort of developing under the hood. We write the majority of our code in Python, so we're trying to make a sort of Python ecosystem of different tools. So we have ClipperPython from the guys at the University of York, Concip. So ClipperPython, sorry, does a whole bunch of map tools. Concip from the University of Liverpool, Tempe from Birkbeck. Colin, my fellow CCP-EM developer, developed something called MRC file, which is a small Python module for loading and processing MRC files. And we also distribute the MRC image processing system that was originally developed by Tony Crowther, Richard Henderson, and Jude Short from the LMB. And we've written a couple of Python wrappers for that. If people are interested in using that more, then we can provide additional wrappers for it. Okay, so just to finish up, there's a couple of things kind of on the horizon that we're looking at. So as I mentioned before, the way that we're sharpening maps with a single B factor is suboptimal. So Iron's developed this algorithm called LockScale, which is a reference-based density scaling, which allows you to do local sharpening. I won't say any more about this because we're fortunate to have Iron here with us, and he'll explain about it this afternoon. But this is now in CCP-EM if you run it in alpha mode. And we're developing it to add the new functionality that Iron's working on at the moment. In the future, we're going to try to sort of broaden our horizons a little bit and go into tomography. We'll provide tools for tomography. So we're working with Mark Basham, who's hiding up there in the wings. So he's written a program called Servos, which stands for Super Region Volume Segmentation. And this is a tomography workbench for identifying areas in tomograms, and he's going to speak about this tomorrow. And then also hiding up there next is Ben Himes from Pei-Jung Zhang's lab in Pittsburgh, and he's developed a package of tools called EM Clarity, and this is an image processing package for high-resolution heterogeneous tomography that he'll talk about tomorrow as well. One other heads up, you might have seen people flailing around outside. So we're very lucky to have Paul Emsley and Hamish Todd here. So Paul, you may know, is the developer of Coot. He'll be speaking later on in the conference. And Hamish is a PhD student from Edinburgh who's working on the sort of virtual reality environment for Coot. And he's very keen for you to come and test it with him. The idea is that this is a serious extension to Coot, not just for playing with. The idea being that by immersing yourself in a structure, you have a lot more real estate to identify and to give people cues to help build models better. So they're very interested in your feedback, so please go see Hamish outside in the breaks. Okay, so I think that's me done. So I just want to say thank you to everyone that we work with. And yep, thank you for coming and enjoy the conference.